Lecture 8, Transformation Law, is a definition of a tensor. Now, transformation law in intrinsic geometry is effectively the defined property of a tensor in differential geometry. Suppose you have a tensor of time Rs, the same notation as we put in the previous lectures. So this is a type Rs on a manifold M. In a given coordinate system xi, and recall the xi are labels that belong to the manifold or in the chart. So the components are expressed as, you see, these are the same colors what I did in the previous lectures. So this is a pumpkin orange here. So this is I1 to IR, J1 to JS. If you change coordinates to another system, YK, the components must transform in a specific way to ensure that the tensor is also a geometric object which does not depend on the coordinate chart. See, that's the definition of a tensor. Tensor is a map. The transformation law is like this one over here. Then there's in this case, in intrinsic differential geometry, a tensor Rs at the point P belongs to M is formally defined as a multilinear map. You see the same colors, these are times, okay, and these are the covectors, okay, R covectors and these S vectors. And the blue one, this is a domain, this is R is the codomain. You see, this will emphasize, okay, on the examples that we gave on the previous lectures. Now you see in the next lecture 9 that Christoffel symbols gamma ijk, this is Christoffel symbols of a second kind. You see, this is not a tensor. You see, I will show this, the derivation to show this does not transform, don't obey the law of transformation, which we can say that is not a tensor.